Okay, so in this video, I will explain you how to use LTSpice, at least to perform the first drawing. The first tutorial that I want to discuss in this video is about how to draw circuits in LTSpice, in particular, how to perform a transient simulation. This means that we are going to extract how voltage and current change in time. So as you can see, this is the first uh, the main window of LTSpice. And here there are a few buttons which I will explain soon. But first of all, we have to start to draw a new circuit, open a new project. So I will just click here, and then you can see now it become all white. You may have some dot here, which is the grid. It doesn't really matter. You can remove it later on. I think maybe there is, there is an option here. If you right click it here, and then you click view, you can show or hide the grid, which are this dot here. In my case, I removed it. So yeah, you can remove it. You can decide anyway. And so what we are going to start now is to draw an RC circuit. And we are going to look about uh, how to perform a transit analysis. In particular, we want to see the charge and discharge of a capacitor. So first of all, I'm going to draw to place the resistance and capacitance here. This is where we are going to draw the circuit. So here there is the symbol of the resistance. Click there. Then I'm going here. You can see, depend on my mouse, the position of my mouse, then I can place in different position. I want a horizontal resistance. So I press on my keyboard CTRL plus R, and you can see it rotate. Okay, CTRL and R at the same times. The button R, the key R on your keyboard. So you see, if you press that, then it should rotate the resistance. You press it here, and then I'm able, LTSpice let me also automatically place another one, but I don't want another one. So I right click with the mouse, right click, and disappear. Then I go to the capacitance symbol here. I click there, and then I press left click with the mouse there. LTSpice one that I build another one, but I right click to stop. Now I have the two components, and I want to place the voltage source, which in my case will be a constant voltage source. So I go here, component, and then here search for voltage. And this is the symbol for voltage source. I click OK, and then place it here with left click and right click to stop. I have to connect them. So this is the wire button here. Click, left click, and left click to connect the components. So you can see the square here are the terminals of the components. So you have to connect the different terminals. Okay, it's very important that you connect the square of this resistance R1 to the square of this capacitance C1. So if you do that, then they will be electrically connected. So I click here, and then right, left click, and left click. Finally, I should connect these two terminal. Left click, left click, left click, left click. Yeah, this is a possibility. Okay, and to build a circuit. So now I can still place a wire. If you can see, if I left click there, but I don't want to place any wire. So right click and right click again to stop to draw wire. But remember that LTSpice want to know all the time which is the reference node, as we discussed at the lecture. The reference node is usually the one which is connected to the negative terminal of the power supply. In this case, is V1. So we take the ground symbol and we connect to that part of the circuit. So I place it here, left click, right click, wire, left click, left click. And you can see there is a node now. So I connected the ground to that point. So right click, that's okay. So if I click on the screen like this with the left click and I keep it pressed and I move up and down, then I can move the circuit up and down. So if I want to move along the project, then I can do that. I release it, and that's it. Yes, so There is also another way to draw the circuit, which I want to show you too, and this is the one we will use. Again, this connection here, it means that this point here of the capacitance connect to ground, and this point is the connect to ground. So we can remove this one here, okay? With CTRL X, we should appear then a scissor. You click here with the left click and you remove that connection. But then we know that this one should be connected to ground. So I do CTRL C for copy, see, there. And I press there in the ground. You see now I copied practically the ground symbol and then I push it here in this point here, there. This one also is okay to draw in this way because right click, because as you know, point of the circuit with the same label or same symbol, they are connected physically together. So this point is like connected here, okay? But I prefer to put the ground here and here. Is the same, okay? Just to show you two possible way. But the important is that you always draw the ground, okay? I will show you what happens if you don't. Okay, so now let's give the value to these components. You go here in this R, right click, and here you put the value of the components. Here we choose 1 kilo, 1K. There is no need that you write ohm, okay? 1K is okay. You go here in the C, right click. Here we'll do 1 U, which means 1 micro, okay? 1 microfarad, okay? And here we can put, for example, 5 volt, 5. Which means 5 volt. You don't have to put the unit again. Healthy Spice understand automatically that. Finally, we want to measure the voltage across the capacitance. This can be done also like this, but I definitely usually suggest to put labels. So when we plot the waveform, we have that the waveform will have a name. Okay, so it's easy to understand which waveform we are talking about. So, but again, I won't do this now, so you can see why we need a label, okay? But I will show you to you how to add the label later on. So, but this setup is sufficient for doing what I want. So what I do is go in here, simulate, edit simulation command, CMD. And now I have to tell LTSpice how long will be my simulation. So how much time in the simulation time I want that the simulation will run. So again, I want to just see that the capacitance charged completely, okay? Let's say 99%. So you know that the capacitance charge as soon as it passes 5 tau, right? So the question is here, how much is 1 tau? 1 tau is equal R times C, and R is 1K, C is 1 micro, so tau is 1 millisecond, okay? So since I want to see the capacitance mainly charged at 99% more or less, I need 5 tau, so 5 times 1 millisecond is 5 milliseconds. So here write 5M. And time to start saving data. So I want to start to save data from 0, so from the very beginning of the simulation. And maximum step, we will see later on what is this parameter. For the moment, leave it do not set anything here. Also the other option, let them be there. So click OK. Now you see it appear in instruction. Place it, for example, here. It doesn't really matter. This one is instruction that tell LTSpice which kind of simulation he has to do. So transient simulation, start from 0, and length 5 milliseconds. So duration 5 milliseconds. So, okay, sorry for that. Is an email. Let me close. Okay, and let's go to play the simulation. So here, click the guide that run, and you can see now it appear a new plot where I will see the waveform of the circuit. So here I like to place the waveform on the right and the circuit on the left. So what I do is window here on the top, and then I place tile vertically. In this way I can see better my waveform. Also this one, usually I want to see the circuit as large as possible. So what I do is click before here, left click here in the left window, and then click this lens here. So I will zoom until the circuit will fill all the window. You can see now it's very large and it's very clear. So now I want to measure the voltage across the capacitance here. You see now when I go to the circuit, there is one probe, the symbol of one probe. So if I want the voltage, then I have to click here, because if I put, this is practically correspond to the positive terminal of the voltmeter, right? So, and the negative terminal is always connected to the reference node. This automatically LTSpice do this, okay? So you have to just put the positive terminal of the voltmeter. In this case, should be here, right? Because I want to measure the voltage across the capacitance. So I click here, left click, and this is the waveform that I get for the voltage across the capacitance. As you can see, this line here represents how the voltage across the capacitance change in time. And the name of this line is VN002, because this node here is called N002, is the node 002. You can see the name here on the bottom left. Maybe I can also spotlight, yeah, like this. You can also see the name here on the bottom left of the of the um, of the window. What kind of name is the point where I'm pointing. You can see when I'm here, you can see in the bottom left there is written VN002. That is the name of this node. This node is N002. So of course, when I have many waveform, like I can plot also here, I do not remember what is VN002, what is VN001. So it's much better to label this node with a name that I know. So in order that here I can immediately see what is the waveform that I plot, okay? So what I do is to make it more clear. You can see I can also add currents. If I click on the components, over the components here, I have also currents here and so on. So the current is a little easier because it tell you the current through which component you're measuring the current. So this is the current through C1, this is the current from R1. However, observe that this is the symbol of the amperometer. Observe that the current that you're plotting has the direction of the amperometer shown on the on LTSpice. You see now it's from right to left, okay? And if I plot this one, of course it's negative, okay? Because it's going in the opposite direction of the real current, because the current is flowing from the positive terminal of the power supply. So if I go here and I click here, you can see the amperometer measure on the current on the other direction. So, but the real current, you know that is going in this direction like this. So this one has to be negative. Here instead, you can see that the current is positive because at the same direction of the real current, the current is going like this, right? So be very careful about the direction of the amperometer. Anyway, as I was saying, when you have many signals, at least in the voltage case, you can see there is VN002, VN001 is a little difficult to understand which waveform is plotted. So what I will do is close this one, and I will start to put some label here at least over the capacitance to make more clear what kind of signal I will have there. So I click here in this button here, and here there is net name. I can choose, for example, V out, because that is uh, the output probably of my circuit. So I click it here, left click, right click, then I create a connection between here and here. Now the voltage at this node here will be labeled V out. So I can distinguish very well when I have the plot. So I run it again with this guy that run here, click here. I want to make them vertical, so window, tile vertically, and then I click here. Okay, any point, it doesn't matter, okay? These are electrically the same points. Click here. As you can see now there is V out. So I immediately know, I can immediately distinguish V out from VN001. In this case, you can see they overlap each other, so I cannot see it very well, the difference, but in general, it's much easier, right? So if you want to remove this waveform here, the blue one, you right click here, and then you click here, delete trace. Yes, so now the question is, why am I not seeing the charging of the capacitor voltage? Because that is what I was expecting. And again, this is the point of this simulation that I'm doing now is also this one here, is that the simulation in this case, it gives you an unexpected result. So you don't expect that the voltage here is constant, but you expect that the voltage increase exponentially. And if you did not know from the theory that the capacitance charge exponentially, you would have guessed that this plot is correct. And for this reason, again, as I say in class, you should never trust the simulator without having an estimation or a guess about what will happen in the circuit, because otherwise you practically will believe blindly to the simulator, which, if not set correctly, will give you the wrong answer. Like in this case, you can see, in this case, we have this constant voltage, which is not what we were looking for, and in this case is not correct because the simulator was not set correctly. So it's very important that you do not use the simulator without knowing or have a guess about what will happen. Otherwise, the simulator probably will give you the wrong answer and you will believe that that is correct. In this case, it's very easy to understand that it's wrong because, again, you know what will happen. But in another case, when you have a new circuit, uh, and if you don't have any guess, then you will just believe the simulator, which probably will give you the wrong answer. Okay, so said that, we have to understand what is the problem in the simulation. The problem is the following. LT-SPICE performed the transient simulation in two steps. The first step is solving this circuit here in DC. Or in other words, what does it do is substitute all the reactive components with their equivalent in DC. As you know, in DC, the capacitance is an open circuit and the inductance is a short circuit. So what does it do? The first step that it does, LT-SPICE, is replace this one with an open circuit. You don't see this operation, but in the algorithm of LT-SPICE, it happened this as first step, okay? So the first calculation that LT-SPICE does is replace this capacitance with the open circuit. So you understand, and then it calculated the voltage and the current. So you understand that if I substitute this capacitance with the open circuit, then the voltage here at V out is of course 5 volt, right? Because if this one is an open circuit, no current can flow, so no voltage over R1. So the voltage over R1 is 0. So the voltage V out has to be equal to the 5 volt. And after that, after he calculated the voltage, okay, uh, when the capacitance is open circuit and the inductance is short circuit, it start to run the transient simulation. It start to evaluate the circuit in time, okay? But of course, in our case, if this one, if the simulator calculate 5 volt, okay, after the DC operating analysis, so after the first step, and then it start to run the simulation in time, this one is already 5, right? So the capacitance won't charge it anymore. This is why we see here 5 all the time constant. Remember, at 0, okay, at 0 here, I repeat it again, at 0, the LT-SPICE substitute the capacitance with an open circuit and the inductance with the short circuit. After that, it starts to run the simulation. So at 0, if I substitute this one with open circuit, the voltage here is 5 volt, I explained it before, and then it starts to run the simulation, but the capacitance is already charged at 5 volts, so it remains always 5. So this is the problem. So to solve this issue, what you have to do is tell to LT-SPICE to skip the first step, the one where he substitute this capacitance with an open circuit. And again, this step is called DC operating point. Okay, so it's calculating the DC operating point. But we want to skip now this step. So we have to skip the DC operating point calculation. Okay, we have to tell this one to LT-SPICE. So we go here to simulate, we go here to edit simulation. And here you can see there is One last item, skip initial operating point solution, and we have to click there. So if you check that box, you will tell to Spice to avoid the first step that I was mentioning to you before. Then we click OK, and finally we are going to simulate again. Let me move this label here so it's more clear. So we're going to simulate again. So we click here, and finally we have our amazing waveform that we were expecting before, right? The correct one. So we were expecting that the voltage across the capacitance, or V out, will practically charge almost at 5 volt. Again, after 5 tau, you have 99% of the total value. Okay, so now finally we found the correct waveform. We want to plot also the current. Again, what am I expecting is that the current has sudden peak here and then is dropping down, because at 0, okay, the voltage over the capacitance is 0. So if I solve the Kirchhoff law voltage here, all the 5 volt have to drop here. But if all the 5 volt drop here, then I have also maximum current at 0. And then little by little this capacitance charge, so the voltage here increase, the drop voltage here decrease, and then the current also decrease, right? So if I click here, which is the current over the capacitance, as you can see, it has a sudden peak here and then drop here. This is again is what I was expecting, so I'm quite sure that these results are correct. Great, so at this point, I want to show you what would happen if I didn't place the ground, because it's an error, a very common error that you sometimes do. So what I will do is just close this one for the moment, and then remove here the ground symbol. Again, I pressed CTRL X to let appear the scissor, and then I click here and here, right? So right click, and then now I'm going to connect them with a wire. Yes, so here. And then I click here, and click here. Right click. So let's say that you build this circle like this and you forgot the ground. I click here in this run simulation. As you can see, LT-Spice tell you actually, the circuit does not have a conduction path to ground. Please flag a node as ground. So if you don't have any ground symbol in the circuit, LT-Spice will tell you and warn you that there is no ground and will not let you do the simulation, okay? So it's very important that you perform the simulation. Again, I put the ground there, right click, I take a wire and I connect this one like this, right click. Now I press the left click here and I bring it down the circuit. Okay, and yes, so another things, I run again the simulation. I do it tile vertically again. I plot again the voltage and the current here. Now I want, for example, I want to know how much is the voltage on the capacitance after 2.5 tau. So again, tau is 1 millisecond, so 2.5 tau is, for example, 2.5 millisecond, right? And I want to know the voltage. So of course, here I can see this is 2.5 millisecond, and then I'm going up, so it's approximately here. I can say it's between 4.5 and 5, but there is a more precise way to do this calculation, to have this value here. I can click here with the left click, and one cursor appear. You see this new line here appear. If you go over this line, it appear 1, which means cursor 1. There is now a cursor. So if I left click and keep it pressed, then you can see that I have my cursor that is moving there along the voltage curve. So now I'm looking about the x-axis and I'm going around 2.5 millisecond there. And here in the bottom right, you can see here, there is a mini window where I show you the x-axis, of course, and the vertical axis, the y-axis. So at 2.5 millisecond, you have 4.59 volt, okay? So you can use this cursor to find the precise value of the voltage over the signal that you're interested in. Of course, in this case, you have two signals, so you may want to use a cursor for measuring the voltage, but at the same time, you may want to use another cursor for measuring the current at the same time, right? So I click here and sorry, I click here. If I want to cursor, I click here, right click, then here I do attached cursor, first cursor one, okay? And then here, right click, attached cursor, cursor two, and then click OK. So now I should have two cursor here, one here, you can see for the voltage, and let me see what it is, and this one here. You see in the current, I have another cursor there. And so I place this one in the, now I'm in the curve of the current here. I put it at 2.5 millisecond, and also the cursor for the voltage here, I put it at 2.5 millisecond there. And you can see that now they are aligned. And you can see here I have the cursor for the voltage at 2.5 millisecond, the cursor for the current at 2.5 millisecond. This is the voltage at 2.5 millisecond, and this is the current at 2.5 millisecond. So this is how to get some value from the plot. And yeah, so it's pretty simple and straightforward. As I said before, if I go, you see now I'm in the window here, but I cannot see the amperometer neither the voltage. This is because you are selecting this window here. You see, this is more dark blue and this is bright blue. So my control is in this window here. If I want to see the amperometer or voltmeter here, I have to before click on the window. You see now become dark blue and this is bright blue. And then I have appear again the amperometer symbol and voltmeter symbol. Again, if I, for example, click here, I can also get the current in the circuit, but in this case, the current is in opposite direction, as you can see from the amperometer symbol. So what I'm expecting to see is a current that has a negative peak. So it's the same waveform, but in the negative, so mirror in the negative side. So if I click here, as you can see, that is what I was expecting. The current is going like this and doing like this. Again, I maybe did not emphasize very good before, enough before, but in the left side of this plot, you have the voltage axis. In the right side, you have the current axis, yeah. And here, of course, in the x-axis, you have the time. Here you have the label of the different waveforms that are here in the plot. Each waveform have different colors, so you can distinguish them, and also the name here is different, right? Great. So at this point is quite important, is quite useful to know how to export this data. In my case, what I want to export is just the voltage and the current through the capacitance. So I remove now this current here. So right click and delete trace. And yeah, so click here again, left click, and the lens. So I click here the lens zone full extent in order that my plot is practically filled by the two waveform in the correct way. Okay, so if I want to export this to waveform, it's not difficult. You can right click here and then you have file, and then you have export data as text. And then you can just find here the point of your the folder where you want to save the file. So you browse it in your computer, and automatically here it will be highlighted V out and IC1 because are the two waveforms that you can see here. But there is also the list of the other waveforms that are in the circuit. In our case, we just need V out and IC1. If you want IR1, you have to just click it there, okay? And then click OK. In our case, we want just V out and IC1. So here, click OK, and there, and it will be saved wherever you want in the in your computer. So let me just open it. So I'll stop share it 1 second. Okay, so I now have, I think you should be able to see my screen with the Word file. I just opened the file where I saved practically the file that I exported, the data that I exported from LTSpice. And it was a TXT file, as you can see here on the top. And these are the data saved in the TXT file. So we have 3 columns. The first one is the time, the second is the output voltage, and the third one is the current. I can see here, you see, this is the order of the wave. And yes, so it is important that you know this order, because then if you want to import it in Matlab, which we are going to do it now, then you need to know this kind of like the order of the column. So what is the meaning of each column? Okay, so keep in mind this order of this column here. And okay, so now I am in the window of Matlab, and my purpose is to import the data that I exported before from LTSpice, so the TXT file. I want to import it in Matlab and do a scientific plot of the waveform that I get it. Remember that one thing I don't want to see in the obliques and also in your project report, I don't want to see any screenshot of the waveforms in LTSpice. That is something that is not good for a high quality report, and so this should not never be done. You always have to export any waveform, as we did last time, from the oscilloscope, from your measurement tool, or from LTSpice to Matlab, and then you plot it in Matlab, because Matlab give you scientific way to plot the data. So so in order to plot the data that you have in Matlab, you have to download a script from the canvas. So I will let you know if you don't know where it is. I will let you know that. You will find it in the lab section or in the software section. So please double check both parts. But again, one will be called plot LTSpice data in Matlab, subplot, and the other is called plot LTSpice data in Matlab YY axis. We will start with this one with subplot. Remember that once you download it, you have to save them in the same folder where is placed your exported data from LTSpice. So my suggestion is create a folder where you, for the lab 3, where you where you save all of these 3 files. So this one here in the top is the file exported by LTSpice. This one here is the, and these 2, they are the file that have been downloaded from the canvas, the script that I provide you in canvas. So let's start with the subplot first, and I will describe what will going on, what you have to do. So I'm going now to share with you. So if you double click there in plot LTSpice, if you double click in plot LTSpice data in Matlab subplot 1, then you should get this other window here that I hope you can see. So you should be able now to see the script, so the code. I will just double check it. Let me see. There. Yeah, so I suppose you should be able to see that. So you can see there is a bunch of code, which is practically the code which is inside the subplot plot LTSpice data in Matlab subplot.m file. The first 3 rows, they just reset and remove all the data before. Practically, if there are some data saved in Matlab, you clear them. If you have some figure open in Matlab, you close them. And practically, you reset Matlab in some way. This one are the settings that are used to make the plot look nice. So set the font, the width line, the marker size, and so on. So don't touch this. And this instruction here will tell you, tell to Matlab that you have to read a file txt, okay, starting with the row number 1 and column 0. You start from the, remember that our file is divided in, maybe I can also open it here, maybe. Let me see if you can actually see that. So I think you can see here, I double click in the draft1.txt in the Matlab window, and Matlab open that file, draft1.txt, which is the data exported. You can see there are 3 columns, and yes, so here this is contain all the data. Let me see. So my point was that you see the first row in this file, the first row is practically 3 label, and we don't want to read this 3 label, so we have to skip 1 row. Okay, so we have to skip the first row, and this is what happened in that part of the code that I showed you before was written 1 and 0. So I will go back now there, but my point is that we have to skip this row because the data start from the second row. Okay, from here, this is the line 0, and this is the column 0, this is the column 1, this is the column 2, and this is the row 1. So we have to start from row 1 and column 0. Okay, so then I go back to share the other here. So I think now you should see my code. So this is the meaning of this 1 and 0. So we start from the 1, row 1 and column 0. So we skip the first line where there are only labels. And then once we, this instruction, read all the data inside of the TC file and then put it in data, which is a variable. Okay, we create a variable, part of the memory of your computer, which is called data. You create a label called data and you store all the data there. Practically what will happen is that this data will have 3 columns and many rows as shown in the file that we opened before. So you know that the first column contain the time, and this instruction here say, I take the table data, I select all the row, and I take the first column, okay? And then I put all of the data in the first column in a variable called time. This one say, I take the table data and take all the data in the second column, and then put it in one variable called VC, because remember the second column is the voltage over the capacitance. So I save all of those data in a variable VC. And then here I have another, I take the table data, I take all the data in the column 3 and for every row, and I save it in a variable called IC. So now I have 3 variables which contain only the data for the time, only the data for the voltage, and only the data for the current. Finally, these are some bunch of code for plotting the data on Matlab. So the only thing that you have to know is that this figure instructions say that Matlab has to create a window for my figure, for my plot. This subplot say to Matlab that you have to devise this figure window that we just created. How? How is defined by this number here? You have to imagine that figure window, okay, we just created as a table, okay? So the first number is the number of row, the second is column, and the third one is the part of the table where you want to draw. So this instruction here just tell you to take that figure window that we just created and divide it in 1 row and 2 column, okay? 1 row and 2 column, and then you have to start to plot in the plot 1, okay? If you divide this window in 1 row and 2 columns, so you will have 2 places where you can 2 box where you can plot your graph, and we are going to select the place number 1. Let's call it like this. And then this one is just instruction that tells to plot. So remember, when you write plot, here this is the x-axis, which is the time, of course, and this is the y-axis, which is the voltage of the capacitance. So in the plot, let's call it number 1, you want to plot the voltage of the capacitance. This one tells you that the color of the curve will be black with a K. K means black. And this one means that it will be a continuous line. We add also the label for the y-axis and x-axis like this. And then here, what do we do is we tell to Matlab that we want still divide. We still have the same organization. You can see here 1, 2, and 1, 2. So we still 1 row and 2 column. But in this case, we are going to draw the plot in the second column. We select the second box. And then in the second box, we plot instead the current x-axis and y-axis. You see, time is the x variable and y is the y, and IC is the y variable. In this case, we draw the curve in red and we use a dashed line. This is the symbol for the dashed line. And then we add also the labels. So here, what I do is click simply run. But the problem is before to click run, you have to do a modification because as you can see, I call the file that I want to read RC charge. Now, in your case, if you did not change any name or if you set any other name, you have to put here the name of the file exported from LTSpice. So this one is the only thing that probably you have to change. If you call it RC charge, then you can leave it everything like this. You can also modify the name of your file in RC charge, so you don't have to modify the script. Or you have to just modify this part of the code and you change this part with the name of your file. After that, in my case, it's called draft one here in this example. So I click draft one and then I click run, okay? And then it will plot. So I click run here and I will show you then, I will share now what it come out. So I hope you can see now the window of Matlab that come out. I make it larger for me. I don't know if you can see that it's becoming larger, but you can see that there is in the left, so you see the figure is divided in 1 row and 2 column. You see, like a table. In the left side, in the box 1, we plot the voltage across the capacitance, and instead in the box 2, which is the right one, we plot the current, okay? So you use a subplot instruction to plot into different plot. This is for the this is for the voltage, this is for the current. Here you can see the x-axis is in 10 to the minus 3. It means that this one is this one is 2 milliseconds, 4 milliseconds, 6 milliseconds. And the same here, 2 milliseconds, 4 milliseconds, 6 milliseconds. Here is 10 to the minus 3. It means that all of these values in the y-axis are milliampere. So 5 milliampere, 4.5 milliampere, 4 milliampere, and so on. And these one are in voltage. Okay, so this is how it is the procedure for plotting the waveform in 2 different plots. I will show you how to overlap these 2 curves here on the same plot. So let me stop to share here. And I'm going now to open the other script. So I'm going again in my Matlab here. So you should see now my main window of Matlab. And I'm going now to open instead this one, plot LTSpice data in Matlab YY axis here. Double click here. And I'm going to share you the new screen. One second, and you share. Should be this one here. Okay, now you should be able to see the screen with the code, this time with the YY axis. So let's see, most of the code is already the same again. This one is already the same, and this one is the same. This one is the figure. This one is a new part of the code, which just set the x-axis and the y-axis in color black, so you don't have to worry about too much about this part. So now the only difference is this part here. So again, with this instruction here, we are going to create one figure, okay, where we can plot the curves. Now, what we're going to do practically is create one plot where there is the left axis and a right axis. So we have 2 y-axes, one on the left side and one on the right side, in order that then we can plot 2 different quantities on the same graph. So the left y-axis is for the voltage. As I showed you before in LTSpice, right? When you plot the current and the voltage in LTSpice, you have the left axis, left y-axis for the voltage and the right y-axis for the current. So this is the same, but you need a little code to tell Matlab that it has to do like that. So y-axis left, tell Matlab that yes to I'm referring now to the left y-axis. So, and then you just plot with the same code that I showed you before. And here I did times 1000. So it means that I multiply the time data, so the data stored in the time for 1000. So it means that here I have to modify actually the unit in my label, which should be millisecond. Because if you multiply for 1000, then the unit will change, right? Here, now I'm telling to Matlab that I want instead plot or refer to the right y-axis of my plot, and then I say plot the current, okay? I will just then, this grid on, it means that you are creating a grid in the plot. So in order that you have some line that guide you, that like a guideline to see, like a grid. Yeah, I will show you soon. So I click run. Okay, let's remember that my name of the file has to be changed if you have a different name for your file. So this is probably the only thing you have to change. So here I write draft one because it's the name that I have for my file. If you have any other name, use the other name. I click run. And now I have to share with you the plot that Matlab show me. I hope you can see that Matlab show me this plot here. You see that both the curve now they are overlapped on each other. The left axis is for the voltage as we saw from the code, and the right axis is for the current as we defined it from the code from the code. And the x-axis is in milliseconds, so you can see there is no any more times to the 10 to the minus 3 here because I did that times 1000. Okay, so this is how to plot two curves over the same graph. So if you want to do this, you have to use y-axis left and y-axis right. If you want instead separate plot, you need to use subplot code. So I hope that this short analysis of of Matlab help you also to understand a little of the code. So once you have one plot in Matlab, I don't know if you know how to save it here, but I will show you that. What you have to do is click here, save, and then save as. You can save it as a figure, which means that is .fig is a kind of type of file that you can open only in Matlab. But you can also decide to save it in BMP, in EPS, or PDF, whatever, PNG. Probably in your case, in most of your case, BMP or PDF is okay. When I do scientific article, I use EPS because I can do um, further processing with other software for adding labels or adding some details, arrows or whatever. But you are free to choose BMP or PNG or whatever. So you have to just save it and save it in your the folder that for the lab 3, for example. And then what you do is just copy that file that you saved into a Word file. Okay. Yeah. So that is how to save the figure. So please try to save both this one here that I'm showing now and also the previous plot that I showed before in the Word file, which contain all your answer. And now I will show you how to save actually the circuit in LTSpice in a correct way. So I have to go back. So stop share. And then I'm going to LTSpice circuit here. So I hope you can see my LTSpice now. Now, in your answer, you also have to save the image of your circuit. So first of all, if the picture is like this, always try to center the circuit in the middle of this window. So click this lens with the cross red. You see, it's automatically centered. And then what you do is right click, and then you do a file, save as, no, sorry, this is not the procedure, is tools, copy bitmap to clipboard. Okay, copy there, and practically you have now saved this picture here. Okay, I can show you now. If I open Paint, for example, what will happen? So share Paint. So now you should be able to see my paint. So if I click CTRL-V, which is paste, you see it appear practically the image of the circuit only. In your case, you have to just do CTRL-V or paste in the Word file with all your answers. So please attach the image there. This is the procedure to copy a circuit from LTSpice. Do not use a screenshot. Do not use the snipping tool. Use this procedure here. And another things, I definitely want to remember you that I do not want to see any screenshot of the plot of LTSpice here, this one here, unless it's explicitly required by the exercise. Every time we show a plot, it should be done in Matlab, not screenshot from LTSpice. If in your oblique or in whatever exercise I ask to show the plot from the simulation in Matlab, from the simulation in LTSpice, you put the screenshot of LTSpice, the exercise will be considered failed. Okay, so do not put screenshot from LTSpice. Especially in your report, I will definitely take out for your final project. I mean, I will take out a lot of points if you put any picture with the screenshot here of the LTSpice. You need to provide a plot which is drawn scientifically and with the same format. Okay, one last thing that I want to show you, I think probably is the last, is that there is one parameter when you do a transient simulation that you have to set it up, which is the time step. We did not do it before. You can access to that one here. So before, remember to click here. This window has to be selected because we want to work here. You can right click here. Okay, automatically will appear the window. I'm not sure if you can see it. Hopefully, yes. So probably also before you didn't see it, but then I can show you now. So this window here that you did not see before, we set it with 5 millisecond and 0 here, but we did not set the maximum time step here. I want to show you what happened when we set this time step here. So if you don't write anything here, then what happens is that automatically LTSpice will decide it for you, and not always that is the best solution. Sometimes you can select this one on your own. Let's, for example, say what happens if I put this one 100 milli, and I will show you now soon. Let's go back to LTSpice and then run again the simulation. As you can see here in the plot, the curve for the voltage and that one for the current is not anymore so smooth, but as you can see here, it's kind of like a piecewise linear function, piecewise linear curve. So straight line, straight line, straight line, straight line, straight line. So made by many straight lines. And this is not very nice because this means that this is an approximation practically. So that time step that I decided before, it tell you how much kind of like is the maximum time step between 2 points of this curve. Remember, the maximum time step is not the time step precisely. As you can see, the difference between this point and this point is not 100 millisecond, okay? So 100 millisecond is it say to LTSpice that you can choose a larger time step, okay? Maximum 100 millisecond, but you can choose any large time step as you want, maximum 100 milliseconds. So LTSpice say, okay, I don't have a much constraints and limitation in the time step, so I make it larger. For example, here I suppose is around 0.8 probably, the distance between here and here. So in this case, if you increase this time step, then you have less precise curve. So again, what you could think about is make this time maximum time step. I have to share it again. What you can think about is make this 100 millisecond or this maximum time step smaller, right? But there is a problem. Let's say, for example, let's put 100 nano, and I pressed OK then, and then here share, and then I run it again. You see, it takes a little longer time to plot it. It's definitely much more smooth and more precise, but it takes longer time. Let's make, I'm now right click there. It appear the window, you maybe not see now, but in your case, you should see. So I set now the maximum time step to 1 nanosecond. And I run it again, the simulation. You see, now it takes much longer time, okay? For sure, the curve that we get now is much more precise because we say now to LTSpice that the difference between 2 points here in this curve has to be 1 nanosecond, but the time to extract the plot is much longer. So there is a trade-off between processing time or simulation time and precision. The more precise you want the waveform, the more time you need. But there is also another trade-off, because if you want a very precise waveform, here you have many points. So when you're going to export this data, you will have a bigger, larger file. So be careful about that. Don't set this time step too small. Otherwise, you will go to export a gigabyte of file, which will take a long time also to upload in Matlab. Yes. So I suppose that this is all for the first tutorial. So now you can look about the text for the lab text, and you can answer to the question which follow the tutorial 1 or task 1.